We are WDK, and our project is Enigma 551. So the Enigma 551 is aimed to represent the historical Enigma machine onto a modern representation, and it is on the FPGA. So the historical Enigma architecture is based on a static wheel, three rotating rotors, and a reflector. So as long as the key is pressed on the keyboard, and then it goes to the first static wheel and being converted to another word, and then it goes through all three rotating wheels, which will step forward one step after each input, and then it goes through the reflector and return to all three wheels to be converted again. So coming out from the last rotor, the letter will be the final ciphered word. So this is our top level architecture, which includes the Enigma top, which is the representation of the Enigma machine, as well as the UART interface that connects to the host computer with the Python program, and also a 7-segment display to represent the rotation of our encryption rotors. So the very this is our very detailed architecture of the Enigma top. So we the same as historical representation, we have a plug board and three rotating rotors, which are controlled by the rotation engine, and also the reflector and the data path that is the same as the original one.
So this is the fully connected demo of our Enigma machine. We're going to be taking this message in the Python, translating it into an array of integers, and sending it to the FPGA. Then the FPGA is going to do the full encoding on it and send it back to the Python for translation, and it will show up right down here on the bottom of the screen. So once I hit send, you'll see these RX and TX lights will start to light up. That's the communication between the two devices. And once that's fully complete, you will see this line down here update. And here you can see the fully encoded message while we maintain the spaces and the capitals. And here is a nice close-up of the board so you can see it all in action. So the journey from a message into the Enigma machine and back starts here at the Python code. I'm going to take you on a quick tour to show you just how everything works. So here at the bottom, I'm using tkinter to make a very utilitarian UI, which you'll see at the end of this, which has a enterable text box where a user can enter the message, a button, and an area using a label that will show what the output is. Once you hit that button with a message, you'll be taken into the show text function here, where we decipher that message and turn it into an array of integers. At the same time, I'm saving the positions of all of the capital letters and spaces, so when we get that message back from the FPGA, it'll be easily translatable back and maintain all of that appearance from when you sent it. Now, once we're done translating it, we take it to the UART function, all the way up here. So in this function, we're sending one element of the message array of ints at a time. During that, in this while loop, we will go through and we will check every time to see if there's been data sent back from the FPGA. If so, we read it in, put it into our final output array, and send the next message. You can see the data to send right here, and then as long as it's not nothing, we write it to the FPGA here at line 35. It'll loop through all of this until it gets to an entry in the int array that actually contains a string called end that we put it in back down here in line 70, so the UART knows when to finish and break out of that loop. Once that's done, we send it right back here where it is translated back for someone to view. that ultimately looks like this.
I'm going to talk about how we are going to do the mapping. The mapping, imagine Enigma Machine, it's rotors. So rotors eventually it will go back to the original position it has. But for Verilog, it's arrays, so it has out of bound index problem. That's why we are doing here. We have double mapping to ensure that the position and the data in will not exceed the index of the array. And for rotation, since the implementation receives letters from UART, we use the negative edge received signal to indicate that the rotate should happen. And based on the architecture alone introduces every time the first rotor rotates 26 times, the second rotor advances 1 time. Every time the second rotor rotates 26 times, the second rotor rotates 1 time. And then when the third hits 26, everything resets. And this is our implementation. We put everything together and then it works.
Let's walk through the simulation for both decryption and encryption, which is performed on rotors front to back and back to front. So the main idea is the output of the decryption should be equals to the input of encryption when I fit in the output of encryption as an input for the decryption. Now let's walk step by step. So in this test bench file, we have a lot of test cases, but let's just go over this first one. I have 0 for data in and 0 for all the positions. So how does it work? So when I add 0 for data in plus 0 of the for the positions of the rotor number 0, I get 0. So 0 plus 0, that's 0. And then I go to the rotor 0 and then see which value is 0 we map to. In this case, we map into 4. So 4 is the output of rotor 0. And then I go back to this file. So I just add 4 as an input, which is the input for rotor 1. So 4 as the input for rotor 1 plus 0 as the positions of that rotor, which is 4. And then I go to the rotor 1 and then follow the same process. And then I get an output, which is the input for rotor 2. So that value plus 0, I get a value. And then I go to rotor 2 and follow the same process. And then I should get an output for the final output. Now, when I go to this file, when I enter 0 for data in, I get 6. In all the test cases, I got different output. So the idea now, if I fit in this output as an input for the decryption, I should get all those values as an output of decryption. Now, let's run the simulation for the decryption and see if that is true. Now, going to the simulation, we see that's true. So 6 was the output of encryption. Now, if I enter that as an input of decryption, I should get 0, which is for the output of decryption, which is equal to the input of encryption. All these other test cases also work as well.
And that is the Enigma 551. Thanks for watching our video and the demo, and a special thank you to Professor Densmore.